A probe is falling toward a black hole. At 10,000 kilometers out, everything looks normal. At 1,000 kilometers, the stars behind it begin to warp, bending around the darkness ahead like light flowing around a stone. At 100 kilometers, the pole becomes unmistakable. And then, at a precise and calculable distance, the probe crosses a boundary it can never cross back. No wall, no surface, no resistance at all. Just a point past which escape becomes mathematically impossible, even for light itself. This is the event horizon. And the question of what actually happens once you cross it turns out to be far stranger than most people expect.
Let's start with what the event horizon actually is. It is not a physical structure. It is a boundary defined entirely by speed, specifically the speed required to escape a gravitational field. Near any massive object, escaping its gravity requires reaching a certain velocity. Leave Earth and you need about 11 kilometers per second. Leave the surface of the Sun and you need over 600. But near a black hole, the required escape velocity keeps climbing as you get closer, until at one specific distance, it surpasses the speed of light itself. Since nothing can travel faster than light, nothing, not light, not matter, not information of any kind, can escape from inside that boundary. That boundary is the event horizon.
Cross it, and the universe outside becomes permanently unreachable. But crossing it is only the beginning of what makes black holes strange. As our probe continues falling, it experiences something called spaghettification. Gravity doesn't pull on an object evenly. It pulls harder on whatever part is closer to the source. Near Earth, this difference is negligible. Your head and your feet experience almost identical gravitational pull. But near a black hole, the gravitational gradient becomes extreme. The part of the probe closest to the black hole gets pulled dramatically harder than the part farthest away. This difference, called tidal force, stretches the probe along its length while simultaneously compressing it from the sides, elongating it into a long, thin strand, not unlike a piece of spaghetti.
For a black hole the mass of our Sun, this would happen long before reaching the event horizon. An object approaches the event horizon, an outside observer would see something seemingly impossible. From far away, the probe appears to slow down, not because it's actually decelerating, but because gravity is warping the flow of time itself, and that warping intensifies the closer the probe gets to the horizon itself. To a distant observer, the probe never quite seems to cross. It appears to freeze, dimmer and dimmer, approaching the horizon forever without ever quite arriving.
But from the probe's own perspective, nothing slows down at all. It crosses the event horizon in a finite, unremarkable amount of time, the boundary offering no resistance, no signal, no warning. Two perspectives, one event, two completely different realities. So what happens after the crossing? Here, honestly, our best science runs out of answers. General relativity predicts that everything falling inward eventually reaches a singularity, a single point of infinite density where the equations simply stop producing meaningful results. But physicists widely suspect this isn't the full picture. General relativity doesn't account for quantum mechanics, and quantum mechanics doesn't yet have a working theory of gravity. Where these two pillars of physics should meet, inside the heart of a black hole, they instead contradict each other completely, which means the true nature of what lies beyond the event horizon remains one of the genuine open questions in modern physics. So the next time you picture a black hole, picture our falling probe instead, stretching, vanishing from an outside view, crossing a boundary it can never return from, heading toward a place where our best theory simply admits it doesn't have the answer yet. That admission isn't a failure. It's exactly where the next great theory of physics will have to begin.